We're going to look at Gibbs free energy and how it relates to equilibrium. And what we're going to look at first is qualitatively, how do we predict a change in Gibbs free energy for a change in an equilibrium system? And we have to go back to that idea of spontaneity, right? And when we determine using Le Chatelier principle, okay, which way is the system going to shift to get back to equilibrium? Right, we're going to look at that as the spontaneous direction, and then we can tell delta G, the change in Gibbs free energy. Remember that Gibbs free energy is negative for spontaneous, and a positive change for non-spontaneous. Okay. So if we look real quick at this quick example, predicting the change in Gibbs energy for the following system if the temperature were raised. Looking at, you should know this as Born-Haber process. Notice that the change is negative, so this is an exothermic, so we can think about heat as being a product. If I raise the temperature, I'm going to be increasing that product, and my equilibrium is going to be shifting back to the reactant side to get back to equilibrium. So in this case, since it is working in the backwards direction, we would predict that the delta G is positive. Now, let's look at free energy and equilibrium from more of a quantitative direction. So, under any conditions, standard or non-standard, the free energy change can be found this way. Okay, delta G is equal to delta G at standard conditions plus R, and remember this is going to be the 8.314 joules per mole Kelvin number, temperature in Kelvin, times the natural log of Q being the reaction quotient. I said it's reaction quotient. Okay. Remember, standard conditions, all concentrations are 1 molar, so Q is equal to 1, and the natural log of Q goes to 0, and the last term drops out. All right, so under standard conditions, Q is equal to 1 at equilibrium. All right, so how do we apply this? Okay. Remember, at equilibrium, Q is equal to K, delta G is equal to 0, and the equation becomes delta G at standard conditions is plus RT, natural log of K, the equilibrium constant, is all equal to 0. Rearranging, we can say delta G at standard conditions at equilibrium is equal to negative RT, natural log of K. You may be able to see where this is going. Oh dear, here we go. Okay, and then we have this very useful equation where if we know the Gibbs free energy, we can calculate K. And we'll be doing some problems in class.